the gravity field strength. So the concept of the field itself, no matter what field you are talking about, the gravity field, the electric field, or the magnetic field, it's a bit strange. So if we are imagining that, in this case for the gravity, that we have an object with a mass, that every other object that is nearby this original object, object 1, is is attracted by these objects. So imagine Earth. It's very comprehensible. So Earth, and then every object that is near the surface of the Earth, and when we say near, we have to use that term very loosely, near the surface of the Earth, is attracted at the surface of the Earth. So this is the effect that forces at a distance has, and forces at a distance exist because there is a field that is surrounding the object. In our case, when we are talking about the gravity, it's the gravity field. When physics 30, when you will talk about electric, it's the electric field, and when we talk about magnet, it's magnetic field. So you see that if you place an object near the surface of the Earth, attraction will happen. This object will go near or to the surface of the Earth. And on the electric field, when you see a charge, will interact with the field, and so will the same thing will happen when we have the magnetic field. Now, if this is the Earth, any object that is around the surface of the Earth is attracted toward the surface of the Earth. So now the gravity field is a field that is surrounding each object that has a mass, and the configuration of the gravity field is something like this. So you have, if you are placing an object here somewhere near the surface of the Earth, the object will have the tendency to go toward the center of the Earth. Now, when you see this, you notice that at the surface of the Earth, those lines, which are known as the field lines, are closer to each other. So those lines are closer at the surface of the Earth, in our case, than away from the surface of the Earth. This tells us that the field strength is stronger at area A than at area B. Now, okay, how do we find out the configuration of the field? And this is for any field, not only gravity field. What we do is we place something that we call it a test object. Test object. This test object, in the case of the gravity field, has a mass that is way smaller than the mass of the source. And the source in our case is the Earth. This is the only condition that the test object should satisfy in the case of the gravity field. So as soon as we place the test object here, we will see in which way this test object is interacting with the source. And in this case, you will see that it will be attracting. And then you place the test object somewhere here, and then you see that is attractive. And then you place the object somewhere in here, and you see that is attractive. On this way, we define that is known as the configuration of the field. Is it clear? Now, again, when we are saying the test of the object is way smaller than the mass of the test object is way smaller than the mass of the source, you have to keep in mind that is in comparison, because a test object can very well, in comparison to the mass of the Earth that we are discussing or we are looking at, or we are very aware that the force of gravity exists. The mass of a human being in general it's easily can be used as the test object, because the mass of any human being is way smaller than the mass of the source that is the Earth. And then the mass of a satellite as well can be considered as the test mass to be used as a test object, because the mass of a satellite is most cases is way smaller than the mass of the Earth. But then when we see even in comparison to the Sun and the Earth, the mass of the Earth can be considered as the test object when we compare it with the mass of the Sun. Okay, so the test object can be any object that has a way smaller mass in comparison with the mass of the source. So in this case, you may say that the mass of the electron, that is 9.11 times 10 to the power of negative 31, can be considered as a test object when we are dealing with a source like us, let's say, okay, our mass, or any human being, because the mass of the electron is way smaller than the mass of pretty much any human being, even the newborns. And the configuration of the field is of any field, no matter what field you are dealing with, gravity, electric field, or magnetic field, the configuration of the field, what is happening in the surrounding, is defined by the direction that the test object is experiencing when it is placed into the field. So in our case, the test object is placed into the field, and then we see in which way is the test object moving, and we will see attraction. And this will tell us that the configuration of the gravity field is, for Earth in this case, is something like this. And those are known as the field lines. And the closer the field line, the stronger the field. Now let's see how do we mathematically measure the gravity field? Because, okay, we can say that in this area, close near the surface of the Earth is stronger than away from the surface of the Earth, but how much stronger? What is the value? So let's see now mathematically what is happening with the gravity field strength. Now, if we have two objects, then those two objects will experience universal force of gravity, as we said before. And this is measured as capital G, mass of the source times mass 1, we can say, or mass 2, doesn't matter, over the distance that they are apart squared. Okay, this is what we said that the universal gravity force is experiencing. Okay, on the other hand, what do we know? If we have a test object, then the force that this object will experience based on the second law of Newton will be mass of the object times acceleration. Are we okay? Now, if we equal those two forces, so then we will have G, mass of the source, times mass 2 over distance squared is equal to mass 2 times acceleration. And since we are dealing with the acceleration due to gravity at any point, we can say that this is equal to mass times g, lowercase g. Okay, so now if we simplify mass 2, why do we simplify? Because it's the same. Then we can say that the gravity field strength is equal to capital G, mass of the source, over r squared. So this is the way that we calculate mathematically the gravitational field strength at any given point. Now, near the surface of the Earth, G is equal to 9.81. And this is supported by the calculations, because if we substitute as the mass of the source the mass of the Earth, and as the radius of the Earth, if we substitute it into the formula, capital G, mass of the source over r squared, we will have a value that is 9.81. We know the units for it are meters per second squared, or 9.81 newtons per kilogram. Make sense? Okay, so let's bring the formula again. Capital G, mass of the source over r squared. So as you see here, the relationship that gravity field strength has in terms of the mass is it is a direct proportion to the mass of the source and direct proportion to the inverse of the distance squared. And then when they are put together, to make them equal, then we add the constant, which is the universal gravity constant, 6.67 times 10 to the power of negative 11. Now, graphically, this relationship will be pretty much the same as the relationship that the force of gravity has in terms of, or in relation to the distance, will be something like this, in which both vertical and horizontal axes are the asymptotes of the graph. But we do not work with something like curved graph in physics. What do? We straighten the graph. And I will go again through the process of straightening the graph. So see, what do we have here? Capital G, mass of the source over r squared. And just to make the visible what is the mathematical manipulation that the distance is going through, I will rewrite it into G mass of the source times 1 over r squared. So now this mathematical relationship that r is going to be our mu x. So in order to have a straight line, what we have to do is to manipulate the horizontal axis into 1 over r squared, and the line will be a straight line in which the slope is equal to capital G times mass of the source. Is it clear? Okay, so now let's calculate the gravitational field strength on the surface of Neptune, knowing all that information that I gave it to you before. What is the radius of Neptune and what is the mass of Neptune? Okay, so using the information that the mass of Neptune is 1.03 times 10 to the power of 26 kilograms, and the radius of Neptune is 2.48 times 10 to the power of 7 meters. We can find the gravitational field strength at the surface of Neptune using the formula capital G mass of the source, that in our case source is Neptune, over radius squared. So this will be 6.67 times 10 to the power of negative 11. And then 1.03 times 10 to the 26 over 2.48 times 10 to the 7. The whole thing is squared up. So now, when you enter this information in your calculator, 6.e to the negative 11 times 1.03 e 26 divide by 2.48 e to the power of 7, close bracket, square. What do you have? What do you have for the value? Yeah. .17 meters per second square. So the gravitational field strength at the surface of Neptune is 11.17 meters per second square. And it is always a gravitational field toward the center of the source. And in this case, the source is Neptune. Okay? Questions? So now we have a question that is saying, what is the gravitational field strength at a distance of 1.914 times 10 to the power of 7 meters above the surface of the Earth? In the previous question that we did on the first part of the lesson, the distance was 12,000 meters above the surface of the Earth. And now we have a gravitational field, we have to measure the gravitational field strength at the surface of 1.914 times 10 to the power of 7 meters. So here is the Earth. Here is the Earth. And this is the surface of the Earth. And this person is somewhere in here, which is a distance of 1.914 times 10 to the power of 7 meters. Now we are measuring the gravitational field strength at this point here. Now, what do you have to imagine if you are going step by step? Is you are placing a test object at this point, and what is happening? The test object is attracted toward the surface of the Earth. This will give you the direction of the gravitational field strength at this point. The magnitude of it is calculated capital G, mass of the source, which in this case is the mass of the Earth, over the distance squared. But this distance is not just the radius of the Earth, or is not just the distance from the surface to the point where this person is standing, but it is adding those two together. So will be a radius of the Earth plus 1.914 times 10 to the 7. The whole thing is squared up. You have now in your data booklet what is mass of the Earth and what is the radius of the Earth. Go ahead, do this calculation and tell me what is the gravity field strength at this point. So based on the calculations, entering the mass of the Earth and the radius of the Earth that the data booklet is giving you, then we have the acceleration due to gravity at that distance away from the surface of the Earth to be 0.612 meters per second squared. And now we have another part of the question. If a person weighs 400 newtons on the surface, what would he weigh at this distance? So as we even mentioned, even in the previous part of this lesson, we said that, mass is a scalar quantity, doesn't change no matter where you are at, from the fact that force of weight, which is the force of gravity, is equal to 400 newtons. We can say that since this weight on the surface of the Earth is 400, that means that this 400 is as a result of the mass times 9.81. And from here, we can say that the mass of the object is 400 divided by 9.81 to be 40.77 kilograms, and some other numbers, but doesn't really matter. So now we take this mass and we multiply by the acceleration due to gravity that is at the distance 1.914 times 10 to the power of 7 meters. So 40.77 times the 0.612, and we will have a force of gravity of about 25 newtons. Is this clear?